w over, well, the only thing left over is that guy there. Yeah. Yeah. Is that mysterious? Everyone whoever feels like they got this, nod. Reasonable? Reasonable? Okay, good. So now I know I can put into here, let me get my unit vector, w modified by its length. And now I know that this length that's in here is actually v dot w divided by length of w. Okay, well, let's just write this. Well, length of w times length of w here, right? What does this denominator then become?
W dot w.
Becomes w dot w, exactly. This is the length of w times itself. That's the length squared. So the denominator becomes w dot w. And the top becomes v dot w. And notice, this is a dot product divided by a dot product. That's a number divided by a number, right? We could always be a little worried that we were dividing by 0. But again, w is a non-zero vector, so w dot w is a non-zero number. And so this is all a scalar, and this is a vector, and so this is going to be our projection of v along w, and we're going to denote this by, what do they call this? They call it v double bar down below. So this is a vector. It's called the projection of v along w, and it's denoted with your regular v vector symbol, but double bars below it. I know, it seems a little funky, but in reality, this is not going to cause too much confusion because you're kind of like, okay, I know what vector I'm projecting along, I know what vector I care about. Notice now, too, that if I define v minus v double bar to be v perpendicular, I can immediately decompose my vector v into two different components, right? I have my component along w, projection of v along w, and projection perpendicular to w. Yeah?
What happens when you deal with more than a few vectors? Then the notation there is to describe which vector is being projected onto which one.
Yeah, you have to take it through context. Yeah, you really do. If you're going one by one, you can just say, that's a good question. And in fact, I'm a little shaky and funky on this. Not shaky. I feel a little funky about this notation in the book. Yeah.
Go look up my linear algebra text.
Yeah.
I remember,
Figure that out, I think.
yeah, I remember in linear algebra they had the
Get projection on the subline with subspaces.
Yeah, but they had
Right.
they notated it as
PRJ sub
Proj, right.
sub W.
Yeah.
We had white hat and everything.
Yeah. I mean, this is good if in context you're not going to be confused what vector you're projecting along. Other than that, I would say maybe projection, yeah, that's right, projection of v along w, or is it the other way around?
That's the one, I believe.
Yeah, well, I'll get back to you on that one too. I'll look in the linear algebra book, David Lay and everything. All right, so this should be enough for you to review 12.3 and do the problems that I have set forth. Let's do the cross product. The first written problem is revised and put up again, and it asks you to actually kind of derive the formula for the cross product. For now, I'm just going to kind of show it to you and talk about its properties. All right, so cross product. Given to, we're going to say, we're not going to necessarily say that these vectors are non-zero or anything about them yet. We're just going to say given two vectors. And what am I calling them here? I'm calling them v and w. And we're going to be in 3 space. This is dimension dependent. So we are only going to be working in 3 dimensions when we're using the cross product. There's only cross product in 3 dimensions and weirdly 7 dimensions. So we're going to stick with 3. I don't want to go to 7. So given 2 vectors in 3 space, we would like a vector, oh shoot, I forgot to say one thing. So given 2 vectors in 3 space, v and w, these are in 3Dville, so maybe they're off the plane, they're somewhere out there in space, right? We'd like a vector that was orthogonal to both. So there's a little orthogonality here and a little orthogonality there, right? This vector here, it forms a right angle with v and w. Even though v and w themselves are not necessarily orthogonal, they just have some angle between them. This is going to be defined to be our cross product ultimately. So the vector that is orthogonal to both is going to be our cross product. But we have to talk a little bit about how we really pick out a vector orthogonal to both of them. First, though, we want a vector orthogonal to both. Note 2 vectors. Is everyone comfortable with the term orthogonal? Orthogonal means you are at 90 degrees to each other. So orthogonal means this, or pi over 2. So a vector here would be up here, and a vector here would be here. Those are 2 orthogonal vectors. Cool. So note 2 vectors are orthogonal, and if and only if, so this means exactly when. If and only if means one implies the other and the other implies the one. If and only if, and we'll call them v and w. They're orthogonal if and only if their dot product is 0. And again, these are non-zero vectors. So how do we see that? Cosine of 90 degrees is what?
0.
0. So if 2 vectors have a 90-degree angle between them, right, then the angle between them is 90 degrees. Cosine of 90 degrees is 0, but we have a formula for what cosine of the angle is. It's v dot w over their lengths. And so, well, these lengths are non-zero because they're non-zero vectors, so it's precisely 0 when v dot w is 0. All right, so this is a little note about this, and that's going to help us know how to even start with the cross product. All right, so we want to find this cross product vector that's orthogonal to both v and w. I claim that we can't just easily pick one, right? Why? Why can't we just easily pick one? Why isn't there a unique one right off the bat?
Because you can have it opposite too.
I could have it opposite, yep, right? That one would still be orthogonal to both the vectors. And in fact, I could make it super long and negative, right? That one would still be orthogonal.
So
Hmm?
you have infinite ones.
I have infinitely many to choose from, right? So initially there is an orthogonal line.
Which is a subspace, right?
That is definitely a subspace if this is at the origin, and you can make it be if you so choose. So initially there's this orthogonal line here. We pick v cross w to be oriented according to the right-hand rule. So what do I mean by that? Like you said, we don't even have necessarily a direction this is pointing, right? This is v cross w, but you said, oh, it could point in the opposite direction. So I oriented according to something called the right-hand rule. So if I have v and I have w here, you do this yourself at your in comfort of your own home, is you use your right hand, and hopefully everyone has one. Does everyone got a right hand available to them? Good, good. That you know, I haven't thought about the inherent discriminatoriness of this right hand rule. You put your right hand, curl your fingers from V to W, and the direction in which your thumb points. This is where I don't draw well.
Professional.
Pretty nice, right? It could be better. The direction in which your thumb points is the orientation for your vector. So we orient V cross W according to the right hand rule. And we give it length equal to, and I'll just write what it is, to length of V times length of W times the sine of the angle between them. So we know which way it's pointing. Now how long do we want it? We want it to be equal to this number here. And this number here is picked randomly out of thin air. No, not at all, right? It's actually got a very specific interpretation. If this is length V and this is length W, then it turns out that the area of that parallelogram is given by, well, base times height. Base is V, height is length of W sine of the angle between them. So length equal to V W sine theta, i.e. area of parallelogram, which I'm going to write p-gram. So the length of the cross product is equal to the area of the parallelogram formed by W and V. Cool. All right. I'm waiting for question? No? Okay. Everyone feeling good about this? Still kind of mid-review, kind of everything looking familiar? Nod your heads if this is yes. Shake your heads if this is no. Okay, great. Perfect. All right, so we've defined the cross product, and now we just need to know how to find it. There is a nice handy-dandy formula for it, and that is going to be given by something straightforward. So V cross W is equal to, right now it's going to look a little ugly, but I'll make it nicer soon. V2W3 minus and V3W2. That's a scalar number, right? This is just multiplication of the components. And this is the directional vector I, right? So let me just write up here, I, J, and K. The I, J, and K are going to represent our unit vectors in the direction of our coordinate axes. So I is the x-valued x-coordinate base vector, J is the y-coordinate base vector, K is the z-coordinate base vector. It's okay? It's okay? Okay, good. And this is going to be a minus here, negative, and I think, let's see. I think I can do this if I do it like this. J plus, I'm setting up my boundaries first. So whenever you work on a problem, try and set up your boundaries first. By the way, if you're going to draw a picture, try and set up the biggest point farthest away you can and work in. If you're going to build a building, try and figure out how far you're going to have to go up first and work your way, you know. Don't just keep building up and eventually it stops. That's how the Tower of Babel happened. And look what happened from there. All right, so we have this number here times that, and this one is, if I remember correctly, yeah, V1 W3 minus V3 W1, and this guy here is V1 W2 minus V2 W1. And we have a really quick and easy way of writing it with something called determinants from linear algebra. Everyone familiar with determinants? Raise your hand. Okay,